Hey guys, so today we will study design of helical spring. So uh, for studying uh, how to design a spring, so we need to know first various terminologies used in spring. So first terminology. The first is solid length. So when the compression spring is compressed until the coils comes in contact with each other, then the spring is said to be solid. And the solid length of a spring is the product of total number of coils and the diameter of the wire mathematically. So LS will be equal to N dash D, where D is the diameter of the wire and N dash is the total number of coils. So if this is a spring, suppose suppose this is a spring. This is in free length. So this is called free length. So this is not compressed. And if it is fully compressed fully compressed then the spring will look like this. So this is called compressed length. So in compressed length you can see we have to count the number of coils is 1 2 3 4 and to multiply with diameter of the coil. So that is called solid length. Now what will be the free length? LF. So second definition is free length. So what is free length? So free length of a compression spring is as shown here is the length of the spring in free or unloaded condition. It is equal to the solid length. So LF will be equal to the solid length, that is LS, plus the maximum deflection or compression of the spring and the clearance between the adjacent coils when fully compressed. So it will be equal to maximum compression, so that is delta max, plus clearance between adjacent coils. So how much is the clearance between adjacent coils? So clearance between adjacent coils. Then the third is spring index. So spring index is defined as the ratio of mean diameter of the coil, that is capital D, divided by the diameter of the wire, so that is small d. So mathematically we can call it as capital C equal to capital D by small d. Fourth is spring rate. So the spring rate of stiffness or a spring constant is defined as the load required per unit deflection of the spring. So K is equal to W by delta. W is the load and delta is the deflection of the spring. So these are the various terminology. And fifth terminology is pitch. So pitch of the coil is defined as the actual distance between the adjacent coils is uncompressed state. So P is equal to free length divided by N dash minus 1. So as we know that free length is LF minus LS upon the pitch of the coil can be also obtained from this relation, that is LF minus LS upon N dash plus D. So LF is free length of the spring, LS is solid length of the spring, and N dash is total number of coils, and D is the diameter of the wire. So this formula also we can use. So this is the various nomenclature of the spring. Now uh, the ends of the spring, there's end connections of the compression helical spring. So ends of spring. So there are various shapes and sizes which are used for end. So for compression spring, for compression, so various ends are used are like plain ends, then ground ends, then squared ends, also squared and ground ends. So these are various ends. And for tension spring, the ends are uh, helical and compression springs. So these are various types of ends for the helical springs. Now we'll see various stresses in helical spring. So stresses and deflection in helical springs. So as we know the nomenclature, I will just repeat it. So capital D is the mean diameter of the spring coil. Small d is the diameter of the spring wire diameter. Then small n is number of active coils. Then G is modulus of rigidity. G is modulus of rigidity. W is the axial load. Modulus of rigidity. W is the axial load. Then tau is the shear stress induced in the wire. Shear stress. C is the maximum shear stress. Maximum shear stress induced in the wire. Then P is the pitch of the coils, and delta is a deflection in the spring. So suppose this is a spring and it is having a load W. So this spring will get compressed. So this will get compressed. Suppose it is having diameter capital D and load is W. So now if we consider the part of compression spring here, the load W tends to rotate the wire due to twisting moment set up in the wire, and thus this will rotate it to thus set up the wire. So thus torsional shear stress is induced in the wire, and a later consideration will show that the part of the spring here is in equilibrium under the action of two forces W and T. So thus we will have twisting moment capital T will be equal to W into D by 2. So it will be W into D by 2. So it is force into radius. So this is distance from the moment. So it will be D by 2. So it is torque. So which is equal to pi by 16 which is equal to pi by 16 tau d cube. So if we make tau as a subject, so we'll get shear stress is equal to 8 wd divided by pi d cube. So in addition to the torsional shear stress, so this is the addition to torsional shear stress inducing the wire, the various stresses also act on the wire. So which are the other shear stress? So that is direct shear stress due to the load W, and second is stress due to the curvature of the wire. Curvature stress. So we know that a direct shear stress due to the load W tau 2. So this we are saying the tau here it is number 1, but we are using it 2 because tau 1 we have used. So direct shear stress due to load W will be equal to load upon cross sectional area of the wire, so which will be equal to W divided by pi by 4 d square, so which is equal to 4W divided by pi d square. And so the direct shear stress diagram sorry so we know that the resultant shear stress will be tau is equal to tau 1 plus or minus tau 2, so which will be equal to 8 wd divided by pi d cube plus or minus 4 w pi d square. So the positive sign is used for the inner edge of the wire and negative sign is used for the outer edge of the wire. Since the stress is maximum at the inner edge of the wire, therefore maximum stress induced in the wire will be equal to tau is equal to 8 wd by pi d cube. If we take this common, so we'll have 1 plus d by 2d. So this is the maximum shear stress induced in the wire. Now as we know that d by d is spring index, that is C. So 8 wd by pi d cube is equal to 1 plus 1 upon 2c. So if we 1 plus 1 upon 2c, so this we will call it as shear stress factor, that is Ks. So it will be Ks into 8 wd by pi d cube. So from this equation it is observed that the effect of direct shear stress is appreciable for springs of smaller spring index C. Also we have neglected the effect of wire curvature in this equation. So this curvature stress we have neglected, so we are not considering it. So it, it may be noted that when the spring are subject to static load, the effect of wire curvature may be neglected because yielding of the material will relieve the stresses. So it will relieve the stresses. So in order to consider the effect of both direct shear stress as well as curvature of the wire, a Wahl's factor stress factor K introduced by Wahl may be used. So the resultant diagram of the torsional and direct shear stress uh, will be equal to like spring index C versus shear stress K. So as the spring index increases, so shear stress factor decreases. So we'll call it as K is equal to Ks into Kc. So K is shear stress factor due to shear, and this is due to the curvature. Total is K. So this we have seen various equations stresses in the helical spring. Now we'll see deflection of helical spring, deflection of helical spring. So in this we have discussed that Maxion shear is developed in the wire. So we know that total active length in the wire L is equal to length of one coil, that will be equal to pi d into number of coils into n. So it will be equal to the length of the wire, and theta will be equal to the angular deflection. So angular deflection of the wire when acted upon the torque T. This is angular, not linear. So the axial deflection of the spring delta will be equal to theta into d by 2. So that is radius into angular deflection. So we know that T by J is equal to tau by radius is equal to g theta by L. This formula, as we know, so theta, if we make theta as a subject, so theta will be equal to Tj by sorry TL by uh, Jg, TL by Jg theta. So where J is polar moment of inertia of the spring, so J is pi by 32 d raised to 4, and G is modulus of rigidity. So if we substitute the values, so theta will be equal to pi by 32 d raised to 4 into G, and T is equal to W into d by 2 into L we have found at pi dn, so pi dn. So if we substitute all this, so we'll get theta is equal to 16W d square n divided by G d raised to 4. So substituting the value of this theta in the equation of delta, so we will get delta is theta into d by 2. So delta will be equal to 8W c cube n by gd. Now c, d by d, as we know it is c, so we can say c cube by d, because here it is d cube and here is d raised to 4. So W by delta will be equal to G d raised to 4, sorry, GD divided by 8C cube n. If I make W and by delta, so the stiffness of the spring or the spring rate, that is W by delta, will be this, which is constant. So this is deflection of the spring. So we have seen various equations for the stresses, and also we have seen various equation for the deflection of the spring. So we will see few examples of this in the next lecture, so which will be more clearer and we will be used to with these equations. So just a second. So here the Wahl factor K, so this formula is given by Wahl, that is 4C minus 1 upon 4C minus 4 plus 0.615 by C. So this equation also we will use in example. So this was given by Wahl. So I forgot to write here, so I have mentioned here. So this is also an important equation. So let's hope we'll see you in the next lecture.